Hi, Basic Calc students. This is going to be day 33 in the packet. Today we're talking about more related rates. And you'll notice that at the very top of the notes it says we're going to go over some selected questions from worksheet A before we recap this lesson. So in fact, I'm actually going to do this entire lesson in the video. It's only 2 pages. And they're both kind of application-y type questions. This first one's about curve sketching. The next one is about related rates. But as a recap, next time you can ask me questions about these two if you have any. But more importantly, we're going to go over, like I've mentioned, some selected questions from worksheet A if you have need some help getting started on some of those. Okay, so what do we got going on in this question? This one involves some curve sketching. You're going to see we have a table down here where we get some information about what f of x is doing. We have some information about the derivative f prime of x, and then some information about the second derivative. It says let f be an even function. And it doesn't seem like that is too big of a deal, but it actually is going to be a big deal for us as we keep reading, which is continuous on the closed interval from -4 to 4. The function f and its derivatives have the properties indicated in this table below. So what I want you to think about is that this is an even function. Notice how we want to think about what the function looks like from -4 to 4, but we're only given information about x ranging from 0 to 4. Which when thinking about, hey, what is this graph going to look like in the end? Because that's the last part, so let's draw a sketch. We have to know that, well, even functions imply that we have y-axis symmetry. So before I go to even answer some of these questions, like figure out absolute maximums and absolute minimums and things like that, I think it's going to be very useful for us to make an f prime number line and even an f double prime number line, because when we go to make our sketch, we're going to start figuring out where the function's increasing, decreasing, has its relative extrema, and then beyond that, where it's concave up and down. And that's all very informative when making a complete and accurate sketch. So let's go ahead and start by making an f prime number line. And even though we only have information from 0 to 4, I'm actually going to use what's happening from 0 to 4 for f prime to think about, well, if this is y-axis symmetry, let's copy that over to the other side. So we know what's happening for the derivative between 0 and 1. Then we have this next interval from 1 to 3, so that will be the next critical point that I have, and then we know what's happening from 3 to 4. And over those intervals, it says that from 0 to 1, the first derivative is positive. From 1 to 3, it's positive again. And then from 3 to 4, the first derivative is negative. So we know that the function is increasing, and then decreasing over these specific intervals. So we can see from increasing to decreasing, because this function is continuous, we know that that's going to be some sort of relative max value. But because of the symmetry that we have to kind of complete this side of the f prime number line as well. So we're going to put -4, -3, and then -1 over here. What I want you to be very careful about is that if I'm increasing from 0 to 1, that doesn't mean I'm increasing from -1 to 0. And I think a quick way to think about that is, if you think about something that's increasing to the right of the y-axis, if it has y-axis symmetry, now it's going to be decreasing on the other side over that interval. So we're going to see the opposite effect when I kind of flip this over the y-axis, where the function's increasing. You're going to get on the negative side of the x-axis, we're going to see it decreasing to create that y-axis symmetry. And that's a little bit tough to wrap your brain around, I think, at first, because it seems like we should just be able to mirror this side of the number line over here. But it actually winds up being the opposite for at least the first derivative. And if we think about where it's decreasing over this interval from -4 to -3, we'll find that it's increasing. So we've got positive and then negative over here. So not only do we exhibit a local max or relative absolute max at 3, we actually also, which makes sense because of the symmetry, have one at -3. All right, before we go ahead and start filling in the information, though, we should probably do an f double prime number line. Okay. So we'll work on the right side first because that's the information we have, and then think about how that transfers over to the left side, the negative side of the x-axis. So for the second derivative from 0 to 1, we're negative. And then from 1 to 3, it's positive. And then from 3 to 4, the second derivative is positive again. So we know that means concave down, concave up, concave up for the original function. And we know that x equals 1 because of the sign change here is going to be representative of a point of inflection, which I think we'll have to come across later on. What I want you to think about is on the other side, with this y-axis symmetry here, do the signs get reversed again? So if it was plus, plus, minus, over here, it became plus, minus, minus. Is that same idea going to happen? And the answer to that is not quite, right? I mean, if you have something for the second derivative that is starting as concave down, something like this, well, on the other side of the x-axis, if it has y-axis symmetry, it's going to also have to be concave down over that same interval. So for the second derivative, you will see a mirror image copied over for these signs right here. So it's going to be negative, positive, positive, working backwards, which means we're concave up, and concave down. So something that we probably haven't explored too much yet in terms of when something has y-axis symmetry specifically, how does that play out if we're looking at an evenly spaced interval surrounding 0? And you can see the key differences between what's happening on the f prime number line for the first derivative and how the second f double prime number line looks a little bit different there. So now that we have all that information, I hope filling in the next few questions should be pretty easy, but then we have to start piecing all this together. By the way, we are given some function values here, so we'll go ahead and include those when we get to making our sketch. But find the x-coordinate for each point where we have an absolute maximum. So we have an absolute max where we go from increasing to decreasing at x equals 3 and x equals negative 3. So we're going to write at x equals plus or minus 3. So if we justify, we know that the derivative at 3 specifically actually is undefined. So it's not even that the derivative equals 0 there, but f prime of x does not exist at x equals plus or minus 3. And f prime is greater than 0 to the left. And less than 0 to the right. So therefore, we have a max at x equals plus or minus 3. Okay. Moving on to our absolute minimum value, the only place where we go from decreasing over to increasing in the first derivative is at x equals 0. So at x equals 0, if you go back up to the table, it's actually not that the derivative equals 0 there, it's undefined. So that's going to make a difference when we look at what the graph looks like there, right? It's not going to be a smooth curve necessarily through these maximum or minimum locations. So that's a little bit different, and I think the concavity will help us to sketch there. So at x equals 0, we know that f prime also does not exist at x equals 0, and the first derivative is less than 0 to the left and greater than 0 to the right, which implies, therefore, we have a min at x equals 0. Okay. So some good justifications there. Make sure that we're including that to justify our maxes and mins. And then we're moving on to inflection points, okay? The x-coordinates where we have points of inflection. So now to justify our answers here, we're going to, of course, use the second derivative test. It's where we're changing from positive to negative or negative to positive, which, of course, in this case occurs at plus and minus 1. So x equals plus or minus 1 are the x values where we have inflection points. And the justification is when we have a change in sign of the second derivative. That implies we have inflection points. Now remember, the change in sign actually doesn't always imply that we have inflection points, but in this case it does because it's a continuous function. So we can probably even make a note of that. Inflection points, oh, and by the way, it is a continuous function, so we know that we're not going to have an asymptote there, and that's our reason for seeing that change in concavity. It actually will be an inflection point on the graph. Okay. And with all that being said, here's what I'll have you do. I'll have you take the information from the first and second derivative, and again, don't forget that we have this key information up at the top here about specific locations, right? So we have the point 0, comma, negative 0.5 for the y-intercept, 1, 0, and then 3, 1. Take those points, plot them, use the y-axis symmetry to flip them over to the other side. Drawn a really nice set of axes. And I would say at this point, hit pause and then come back in and hit play in a second here to see if we get graphs that kind of match up. Now, they should be relatively looking almost the same. There might be one part that looks a little bit different, but for the most part, they should be looking pretty similar to one another, okay? All right, if you hit pause and you're ready to hit play again, here's what my sketch looks like. There it is. So we know that from 0 to 1, we're concave down, but the function should be increasing, right? According to that. So we're concave down and increasing until we get to x equals 1, where we have an inflection point. We're still increasing from 1 to 3, but now we're concave up. And then we have to be decreasing from 3 to 4, but we have to remain concave up. So concave up to concave up, in this instance, to go from increasing over to decreasing, is going to create this sharp ouchy corner such that the derivative doesn't exist at x equals 3. Okay, and we happen to know that this is going to be our absolute max at x equals -3 and x equals +3. Okay. Similarly, as soon as we get this right side, we copy it and reflect it over the y-axis here because of the y-axis symmetry. The only thing we don't quite know is, even though we know we're decreasing over here, we don't know how far down we're going to wind up heading as we approach x equals 4 over this interval. So if you carried yours down a little bit further, that's maybe one of the differences we could have in our graph. For some reason, I think this looks like a fox. Is anyone else seeing fox here? I don't know. I guess I'll check with you guys in class, but it looks like these are the eyes. Here's the little fox nose, and these are all the fox ears. I don't know. It looks like a fox to me. Could be maybe just being a little crazy, but maybe I'm not crazy. Maybe you're crazy with me. Okay, let's move on to our last question for today, which is a little bit more with related rates. And in fact, it's the same type of scenario that we had in yesterday's lesson. We have a 25-foot ladder. It's resting against the side of a house. And the ladder starts to slide down the house with the base of the ladder sliding with a constant velocity, 5 feet per second away from the house. And when the base of the ladder is 15 feet from the house, we're going to determine not 1, not 2, but 3 things today. The only thing we wound up doing in yesterday's lesson was part A, how fast the top of the ladder is moving, and then the velocity of the top of the ladder, which are very related questions, but they are slightly different looking answers there, right? So we'll start with part A. And in fact, I'd actually encourage you at this point to try part A on your own, since it's almost identical. I mean, different sort of values there for the length of the ladder and the velocity that the base is sliding out at, but it's the same setup as yesterday. So to make sure that you're kind of on the right track with these, I would say, you know what, why don't you hit pause, do part A. I'm going to actually just start showing my answers here. So we have this ladder that's 25 feet long. We know that the base x has a rate that it's sliding out, dx dt, of 5 feet per second. And we know that the height y is what we're going to try and find in the end. We're trying to find the rate at which the top of the ladder is moving down. Okay, so we're looking for dy dt in the end. So I think it's probably good if you are still consistent with setting up the given, want, when. I think that's the best case scenario to figure out what we know, what we're allowed to plug in, and what we're looking for in the end. Okay, so what are we given in this case? We're given that the ladder is 25 feet. We're given that dx dt is 5 feet per second. What do we want to find out? We want to find dy dt, the rate at which the ladder is moving down. And then when do we want to figure this out? We want to figure this out specifically when the ladder is 15 feet from the base of the house. So when x equals 15 feet. All right, so to answer part A, we're going to set up some Pythagorean theorem, right? We would get x squared plus y squared is equal to the ladder squared, which is 25 squared. And that ladder definitely is not going to change its length, so we can substitute in 25 squared there. We don't have to call that L squared. But remember, we can't sub in x equals 15 until we've actually found the derivative of this equation. So the derivative with respect to time would be that chain rule step 2x dx dt plus 2y dy dt is equal to 0 on this side, derivative of a constant. Let's start maybe subbing in what we know. So we know that we're looking for the rate when x is 15, and we know dx dt is 5, plus 2 times y. Oh, wait, that's that thing that happened yesterday too, didn't it? I called this in the lesson that hidden unknown. So when x is 15, we weren't told what y is, but we can determine that by doing 15 squared plus y squared equals 25 squared. And nicely, of course, I've given you a Pythagorean triple again. There was a different Pythagorean triple yesterday. This is a multiple of the 3, 4, 5. So if you quickly do some algebra there, you'll get that y equals 20. So now we can sub that in. Okay. So cleaning this up a little bit, let's see, that's going to be a total of 150 on this side. So I'm going to subtract that over and then divide by 40. So dy dt equals negative 150 over 40, which reduces to negative 15/4 feet per second is the rate at which the top of the ladder, it's the velocity of the top of the ladder, right? It's the rate at which the ladder is moving down the wall there. So it makes sense that that's negative because of the fact that we're moving down the wall. And like we said yesterday, you know, that rate does not necessarily match the rate at which the base of the ladder is sliding out from the wall, which is pretty weird, right? But one other quick note here is that we didn't quite fully answer the question yet. This is the velocity of the top of the ladder. But when it asks you, you know, how fast the top of the ladder is moving, when we're talking about how fast something is, that's an application of speed, and speed is the absolute value of velocity. Okay, so we don't have to do any additional work here, but just referencing, if I said how fast is it moving, the answer to how fast is positive 15/4 feet per second. Okay, slightly different way of asking that, but same concept here. Okay, so now we have part A done, and again, that should be very similar to what we did yesterday. The next two parts are going to look a little bit different. One of them is talking about figuring out whether the area under the ladder is increasing or decreasing. So we're trying to figure out what is the rate of change of the area as this ladder slides out. Is the area getting bigger underneath, or is it getting smaller? So for area, we know that area is equal to 1/2 base times height for a triangle. And the base and the height are our lengths x and y there. So if we want to find the rate at which the area is changing with respect to time, dA dt, well, we're going to take the derivative of this side, and hopefully we're going to apply some product rule there for the quantity x times y. So you can attach the 1/2 to the x when you do product rule, or you can just kind of leave the 1/2 out front the whole time. So if you take the derivative here, the derivative of x is just dx dt times y, plus the derivative of y is dy dt times x. And since we've determined all this information already, we can actually pretty easily sub in, and we know dx dt is 5. We're still trying to figure this out, by the way, when the ladder's 15 feet. So we're using this initial condition, 15 feet from the house, determining each of these things under that condition. Okay, so 5 times 20 plus dy dt, we just found in the last example. Don't use how fast. We know that that rate is actually negative in this case. So negative 15/4 is the velocity there, and then times x at this moment, which is when x is 15. Okay. So if we clean some of this up, it would be 1/2 of 100 plus, it's actually going to be negative 225 over 4. Okay. Distribute the 1/2 in, combine those. We wind up getting that in total, dA dt is 175/8 feet squared per second. Just careful with the units here, right? The rate of change of the area would be square feet per second. And because in the end, this wind up being a positive number, we know that the area underneath the ladder is increasing. So maybe that was tough for us to determine, just thinking about it logically, about whether or not at that moment it's increasing or decreasing. But specifically when x equals 15, under these conditions, we get that the area underneath is increasing at this specific rate. And then finally for part C, I'm going to give you a full page for this one, right? Part C, the rate of change of the slope. Okay. So when we think about the rate of change for the slope here, the slope of this line would be, if we think about rise over run, at any given moment, the slope could be expressed as m equals negative y over x. So now that we have a definition for the slope, and again, this could apply at any given value for x and y, but we are still going to stick with when x is equal to 15. We're going to find the rate of change of the slope. So to find the rate of change of the slope with respect to time, we have to find dm dt in this case. And because we have a fraction instead of product rule, of course, now we'll use quotient rule. So it's going to be, in this case, low d high. So it's going to be x times derivative of the top, which is negative dy dt, minus high d low. So when I do minus the high part, it's actually going to be minus a negative y, so we can write that as plus y. D low is dx dt. And then don't forget, for quotient rule, it's over low squared over x squared. And once you have this slope defined and then take its derivative, it's just plugging in the same exact information as before. So dm dt would equal, in this instance, x is 15. We know that in this case, we have negative dy dt. It's going to wind up being positive 15/4. And then we get plus y, which is 20. And then dx dt we know is 5. Okay, so plug those in when x is 15, so the bottom is 15 squared. And you can do as much algebra as you want to clean this up. It's a complex fraction, so if you want to multiply, top and bottom by 4 here to clean it up, in the end, once you're done simplifying, you get that the rate at which the slope is changing is 25 over 36. Okay. So hopefully these different looks at how other things we can discuss with related rates and this classic like ladder sliding from the wall problem. And it's classic because I think this is a common situation that you'll see come up with related rates. It's now the second time in 2 days that we've seen this question. Hopefully this additional information involving how the area is changing, how the slope's changing, based on the calculations we've done, shouldn't extend ourselves too much beyond what we know is happening here. All right. So that's it for today's with related rates. And of course, like I said, next time I see you, we will do some more practice from worksheet A. Have a great rest of your day.